Welcome to the 13th lecture of combinatorics. In the last class, we were discussing this problem. Consider this program segment for I equal to 1 to 20 do, for j equal to 1 to I do, for k equal to 1 to j do. Print something. How many times will the print statement gets executed? So, this is a nested 3 for loops nested one inside the other. Now, the answer, it is easy to see that by the time it reaches the print statement, there will be some value for I, some value for j and some value for k, and these values. So, I, j, k will satisfy this rule, I always greater than j always greater than or equal to k, right. So, the claim is that any a comma b comma c, sorry, right. So, consider the triple a comma b comma c, where a, b, c, everything is in between 1 and n. Say instead of 20, let us take n, a, b, c. That means a comes from the set 1 to n, b comes from the set 1 to n. Here now our problem, it was n was 20. So, now we are taking n is generalize this a, b, c. So, now such that this is satisfied, a is greater than or equal to b greater than or equal to c. Consider the set of this kind of triples, right. Now, you know any I j k, the value of I j k taken as a triple just before printing, that will be from this set, right. That means they will satisfy these conditions that a, b, c, all of them are coming from 1 to n, and also a is greater than or equal to b is greater than or equal to c. It's the nature of the problem. That is what is implied by that for loops, right, the way it is written. Now, the other way, suppose you get any triple a, b, c such that a is greater than or equal to b greater than or equal to c, and a, b, c all are coming from 1 to n, then you know that there is one print corresponding to such a triple, because see in the for loop I will reach the value a at some point of time, because I is running from 1 to 21 to n. So, and then j will reach the value b for that corresponding value of a, because j will run from 1 to a, b is definitely less than or equal to a, by assumption b is less than or equal to a. Therefore, j has to take the value b for when corresponding to the to I equal to a, right. And then when I equal to a and j equal to b, k will also take the value c, because c is less than or equal to b, right. So, therefore, at that time when it reaches the print statement, this particular value of I, j, k will be a, b, c. So, we see that the number of print statements will be equal to the number of members of this set x, y set, such that x greater than or equal to y greater than or equal to z, and 1 less than or equal to x comma y comma z less than or equal to n, right. This is the cardinality of this thing is what we are looking for. So, you see, if this would have been very easy to count if you were just saying x greater than or equal to y greater than or equal to z. That means they are not, x and y cannot be equal, y and z cannot be equal, like that, right. So, then what is the answer? The answer is just, you just take 3 numbers out of the n numbers, see this n, right, 1 to n. So, once you take that number a, b, c, so we can just give the biggest number to x, the next biggest number to y, and the next biggest number, the smallest number to z. That would, because that is for any selection of 3 elements from 1 to n, there is only one way of assigning those numbers to x, y and z, because x has to get the biggest among them, y has to get the second biggest, and so on, right. So, there is no other way. And similarly, for instance, you can see that any pair, any triple corresponding to x, y, z will correspond to only one triple, I mean 3 element set from n. So, finally, the answer will be n choose 3, right, because any selection of 3 elements will satisfy this condition, right. We can assign those members of that 3 set to x, y and z such that this condition is satisfied, right. So, now the issue is that we have this less than equal to. So, then it is easy now. So, what to do is this we are selecting actually x, y, z, right, and x can be equal to y and z, and these things are coming from 1 to n, and then the repetition is allowed. That is what, for instance, we are selecting 3 things from n type of things. N type of things is 1, 2, 3 up to n, right, with repetition allowed. That is what, right. So, you can select say 2 for x and 2 not for x, see 3, because once you select the 3 things, for instance, I select 2, 2, 3. Now, there is no confusion which should be x, which should be y, because the biggest should be x, right, x equal to 3, and y should be the next biggest, second z should be the next biggest. It should be the non from x to x, y, z in that the order in which we write would be non increasing, right, non increasing. It can, the repetition comes means it will be equal, but never increase, right. So, therefore, it is just a matter of selecting 3 things with from n type of things. N type of this is one type, second type, third type, n type, n things, and objects with repetitions allowed. So, any number of repetitions in fact, right. So, you can see that the answer is, because here r equal to 3, k or k or n equal to n, right. So, the type number of types, right. Therefore, the answer is equal to r plus n minus 1 choose r, right, 3 plus n minus 1 choose 3. This is how much, n minus 2 choose 3. This is the answer, right, n minus 2 choose 3, correct. So, now we can see that we can always generalize. So, this suppose the 4 loops were not just 3, for I 1 equal to 1 to n, right, and for I 2 equal to 1 to I 1, for I 3 equal to 1 to I 2, like that we could have written r such statements for I r is equal to 1 to I r minus 1. So, this kind, and then I say print something, right. So, how many times the print statement will be executed? Now, instead of 3 we have r things, right. Then now we are talking about r tuples, right. So, say x 1, x 2, x 3, x r should be selected in such a way that x 1 is greater than equal to x 2 greater than equal to x 3 greater than equal to x r, right. Now, you know, once you select these things, right, the issue here is you can have equal values. So, just from 1 to n you just select r numbers, right, but just that some numbers can repeat, right. So, it is just like n type of things are there, 1, 2, 3 up to n, you can take r of them, but sometimes some numbers are repeating. So, once you select it, there is no confusion, because the biggest should go to x 1, second biggest should go to x 2 and third biggest should go to x 3. If there are ties, we just keep on writing the same number and then till the last, right. So, for instance, if you had selected 9, 8, 3, 3, 2, 4, then we will give 9, 8, right, 4, then 3, 3, 2, like that, and the decrease non increasing order, right. It is not really decreasing here, for instance, is equal, but non increasing, right. So, therefore, it is only a matter of just selecting r things with repetition allowed from n 1 to n, right. So, therefore, the answer is r plus n minus 1 choose r, right, as we already seen. So, when r equal to 2, when we started with r equal to 3 to make it more non-trivial, then we discussed the r equal to 2 case and so that 1 plus 2 plus 3 plus n is the answer, because remember for I equal to 1 to n, for j equal to 1 to I print, right, this statement, how many times print statement will get. So, j when I equal to 1, j will be 1, j will go 1 to 1. So, I equal to 2, j will go from 1 to 2, that is 2 times, and when I equal to 3, j will go from 1 to 3, that means 3 times, and so it is just adding up these things, and this totally this sum will be, this sum number of times the print will be executed, right. Now, we see that we could have also computed in this way, right, when we can put r equal to 2 here, and then what is this happening. So, r equal to 2 here, the value of r is assigned 2. So, that is 2 plus n minus 1, that is n plus 1 choose 2, right, this is n plus 1 choose 2. So, we are seeing that this will be the same as that sum, right, 1 plus 2 plus 3 plus up to n. So, this is what, this is our familiar n plus 1 into n by 2, right, this will be the sum, right. So, in some in other way, this is a combinatorial proof that this sum is equal to n into n plus 1 by 2, right. What have we done? We have observed that when only 2 for loops are there. So, this is actually the number of times the print statement will get executed will be this sum 1 plus 2 plus 3 plus this thing. But another way of counting it is to count all the pairs to two element subsets from n with repetitions allowed. That is, we know that because there are n types of things and r equal to 2, that is 2 plus n minus 1 choose 2. So, this is exactly equal to n plus 1 choose 2. So, this both has to be same. So, we see that this 1 plus 2 plus 3 plus up to n is equal to n plus 1 choose 2. So, that is n into n plus 1 by 2, right. So, therefore, that is why we say that we have combinatorially proved that this sum gives this when you add up these 1 to n, we get this number, right. Now, yeah, so yeah, next one. So, we will consider the next question now. So, yeah, the combinator. So, here is a different question. So, a customer goes into a bar. So, in the bar he sees in the counter there are 15 bar stools. So, in a row, you can assume that in a row there are 15 stools, right, and then he wants to occupy some stool, right, but he looks at the pattern of occupation. He just sees that some stools are occupied, some stools are not occupied. So, he can write down the pattern he sees. So, for an occupied, the first 2 stools are occupied, the occupied, then it's empty, next one is empty, next is occupied, next is occupied, next is occupied, then you see empty, 3 seats then are empty, then occupied, then occupied, then occupied, then empty, then occupied, right. So, from his perspective, so when he looks at, he does not care about who is sitting on the stool, he is only worrying whether a stool is occupied or not, and he is reading O and E, occupied or empty, from left to right, and he can write down on a straight line O E E O E O like that, depending on if ith seat is occupied, he will write in the ith position O. If the ith seat is unoccupied, that means empty, then he will write E in the ith position. So, he says that this is some pattern, right, he observes. So, he will say that now there is a run of OO, first run, then this is just E, that is another run, then there is a run of 4 O's here, and then there is a run of 3 E's here, and then there is a run of 3 O's here, then there is a run of 1 E, then there is a run of 1 O. So, he will say that in this pattern there are 1, 2, 3, 4, 5, 6, 7 runs, 7 runs. So, 15 letters are written, where each letter being either an O and E. A collection of a sequence of O's flanked by 2 E's starting after an E, and then the collection of O's, the sequence of O's till the next E is called a run, right. Similarly, a collection of E's starting just after an O and then running till the next O is encountered is called a run of E's. So, now we are interested, in this question we are interested to count the number of patterns where there are exactly 7 runs. So, this kind of questions come in statistics. So, why this is done is unimportant for us. We just want to find how many patterns will have 7 runs, that is what we are asking. So, we deal with this question in the following way. So, we want to find, for instance, example 7 runs, right. For instance, I can start with an E, right. Then I can keep on writing E's, right. How many E's I can write? So, 1, 2, 3, 4, 5, 6. So, okay, 7 runs I want, and also there is a condition in that problem that yeah. So, there is a condition in the things, in the out of the 15 stools, 5 should be empty and 10 should be occupied. 5, that is the first thing. So, we have 2 conditions. There are 15 stools, that means a sequence of 15 letters is written. Out of that 5 are E's, 5 E's we should see, and then remaining 10 should be O's, right. So, suppose if you write initially itself 5 E's, then we will have to write all the remaining 10 to be O's, right. So, that means we will get only 2 runs, right, because this is one run and this is another. So, we will not get 7 runs. So, this will not be a valid pattern for us, we are not counting this at all, we are not interested in this. So, but we are interested in patterns like, for instance, I start with 3 E's, right. Then for instance, okay, if I start with 3 E's also, we can not do this thing, because then yeah, we cannot create, right. If we can put an O here, start with, then we can put something like this, say 1, 2, say, and then remaining are all is. So, 1, 2, 3, 4, 5, 6, 7, and then till 10 O's I will put. So, this is one run here and another run here, third run here and another run here, another run here, another run here. How many runs? 1, 2, 3, 4, 5, 6. Yeah, so maybe I cannot. How many runs? 3 plus 1, 2, 3, 4, 5, 6, 7, right. 7 runs are there. This is valid, right. So, now how many patterns are valid, in the sense that in the sequence we have exactly 15 letters, each letter is either an E or an O, and then total number of E's is equal to 5, total number of O's is equal to 10, and we are also want to make sure that the number of runs is equal to 7. So, you can notice that if the number of runs is 7, we can do it in 2 ways. Either we can start by E's, if we can start with E's, right, a run of E's, but then how many runs of E's should be there, because total is 7, and after one run of E we should get a run of O, then there should be a run of E's, then there should be a run of O's, then there should be a run of E's, right, total 7. So, we start with 1 E. So, it's by the time we finish 6 runs, then the last is O, the last should be, the next is 7, the 7th one should be E, right. So, if we start with the E's, then there are 4 E runs, right, and 3 O runs. Similarly, if you had start with O, it will reverse. If you start with O, then what will happen is, so you start with O, then you will have to start with E's, next will be E, next will be O, next will be E. So, 1, 2, 3, 4, by the time the 6th run is, that is O, right, sorry, the 6th run will be E, right, because the 2nd is E, 4th is E, 6th is E, then the 7th will be O, you will be ending with. So, there will be an extra O than the E's. So, that means there will be 4 O runs and 3 E runs. So, now we can, and these are disjoint sets. So, we can count the number of patterns which satisfy all our property, but starting with an E run and then add the number of patterns which satisfy all our conditions plus the first run is an O run, right, and this, because these are disjoint set, we can just add them together, right. Now, the question is that what is the question? So, the how many runs are there with how many patterns are there with starting with an E run, right, E, E, O, O, then E, something like this, right, and ending with an E, right. Now, suppose the number of E's here, the first run, let us call x1 number of E's, right, and this is a variable, we can fix a value for x1, integer value, positive integer value, and this should be x2, say number of O's, right, that is x2, and then in the third one, that means an E run, third E run, that x3 will give you the number of E's there, and x4 will give you the number of O's in the fourth run, and x7 will give you the number of E's in the last run. So, we know that x1 plus x3 plus x4 plus x7, that means the total number of E's is equal to 5, that is the part of a condition, and similarly x2 plus x4 plus x6, the total number of O's is 10, right. Now, you see how many ways we can do this thing, but you see this each xi has to be greater than or equal to 1 here. Why? Because if it is an empty one, the run we will not have 7 runs, because if this was an empty E's, then what will happen is this is empty, right. So, this will be a continuous run of O's, that will be counted as 1 only, and this was also, this empty run is not counted at all, right. So, therefore, every run should contain at least 1 E, similarly at least 1 O if it is an O run, right. So, therefore, xi should be greater than or equal to 1. Now, we could have, if xi was just greater than or equal to 0, counting how many, so how many possible ways we can assign values to integer values to x1, x2, x3, x7 is easy, because this is we have seen that this is 5 is the value of R there, the number of types is 4 here. So, 5 plus 4 minus 1, choose 5 will be the value, right. But then now we know that this is just like everything should get a value of at least 1. So, it is like filling the putting the balls in the container such that no box is empty, that is the equivalent problem in the box and bin type. But here we are saying that every x's should get at least 1. So, we can convert the problem to, say, we will define y1, y3, y4 and y5 correspond to this thing, and they should add up to, now they should add up to, so what is this yi? Yi is equal to xi minus 1, right. So, because here each x1 xi has to be at least 1. So, yi is xi minus 1, it should be at least 0, that is all. So, yi has to be at least 0, and only because xi minus 1 is put, now the thing is, when you add up these things x1 plus y3 plus y4 plus y5, we have to also minus from the other side, right. So, 4, this will become 1, right. 5 choose 5 minus 1 5 minus 4 is equal to 1, right. So, our question is like how many solutions are there for this equation y 1 plus y 2 plus y 3 plus y 4 is equal to 1. You see any solution with the condition that yi is greater than equal to 0. You see any solution for this thing will correspond to a solution to the earlier problem if you just add 1 to each of the values. I mean whatever y 1 gets we will add 1 more, whatever y 2 get we will add 1 more. So, that will give a solution to that x 1 plus x 2 plus x 3 plus x 4 equal to 5 problem, because this the total, because we are adding 1 to each of them, this answer also will be 1 plus 4, right. So, reversely conversely, if we get a solution to that problem, we can take a solution because each of them are xi greater than or equal to 1. So, therefore, we can minus 1 from each of them. So, now we will get a corresponding yi which is greater than or equal to 0, and they will sum up to 4 less than what the xi's were summing up to. So, that is because the xi's were summing up to 5, this will correspond to the sum will correspond to 1 here. So, therefore, it is enough to count this, and this we know very well how to count, because r equal to 1 here, and then the number of types is 4. So, our formula says it is 1 plus 4 minus 1 choose 1. So, this is 4 choose 1, right. There are this many ways of selecting your e's, and then this many ways of selecting e's, and then that is not enough. We have whatever our assumptions we are starting with is, therefore, there are 4 e runs, and then how many o runs are there? 4 e runs are there, and these 4 e runs can be selected in 4 ways, as we have seen, right, as we have seen. Now, the other one, so the other question was how many o runs can be there. That is equivalent to the number of ways we can assign values to integer positive values, positive integer values to x 2, x 4, x 6, such that they sum up to equal. So, we see, remember each x 2, x 4 and x 6 has to get at least 1, as we are telling, because they are runs of o's, then they should have at least 1 over there, right. And now, but to convert it to the familiar problem, what we do, we will convert it to y 2, y 4 and y 6, as we always do, and then we will say that they should sum up to 7, because each yi is defined now as xi minus 1, as and then, so the condition on yi is only that yi is greater than or equal to 0. So, therefore, we can apply our earlier this thing with r equal to 7, and there are 3 type of things. So, the answer will be 7 plus 3 minus 1 choose 7. So, this will be 7 plus 2 9 choose 7, right. So, now we can multiply by 4 choose 1 into 9 choose 7. This will be the number of patterns where we start with an e run, right. Now, we consider the o runs, right. So, if we start with an o run, then there are 4 o patterns, o runs, and then 3 e runs. That is why, because we start with o runs, then middles will be e run, and then o, then e, then o, right, then e, right, one then one more o, right. So, let us say the number of o's is x 1 now, the number of e's is x 2, number of o's is x 3 here, same way, this is x 4 and this is x 5, this is x 6 and this is x 7. So, we also know that x 1 plus x 3 plus x 5 plus x 7 has to be equal to 10, because the total number of o's in the pattern is 10. Similarly, x 2 plus x 4 plus x 6 has to be equal to 5, because the total number of e's in the pattern is 5, right. Now, similarly, because the condition here is each xi is greater than or equal to 1, as we were telling. So, we convert it to yi in both cases, yi has to be greater than or equal to 0. So, then so for instance, when we substitute by y 1, y 2, y 3, y 4 here, this will become 6 instead. Similarly, when you substitute by y2, y4 and y6 here, so this will become 5 minus 3, that is 2, right. So, now we can see that the total number of possible ways to give values to y1, y2, y3, y4 is 6 plus 4 minus 1, choose 6, right. 6 plus 4 minus 1, choose 6, that is 9, choose 6. Similarly, the number of ways to assign values to this thing is 2 plus 3 minus 1, choose 2, 2 plus 3 minus 1, choose 2, this is 4, choose 2. Now, multiply them together, because these are the number of ways we can decide the e's, the number of ways we can decide. So, these are the number of ways we can decide the o's, and these are the number of ways we can decide the e's. Now, we multiply them together, we get the number of patterns such that it starts with an or run. And now, after finding this product, we have to sum this with the earlier one we have found out, namely this, right, because this was the number of patterns which starts with an e run, right. So, therefore, if you add these two things together, we will get the final answer, right. So, this is yeah, right. So, this was the this thing. So, the question. So, like that we found out the total number of patterns such that it is composed of only two types of letters, e's and o's, and total number of runs is equal to 7, and number of e's is equal to 5, and number of o's is equal to 10. The strategy was to split them into two disjoint sets, namely the patterns which starts with an o run, the patterns which starts with an e run, and the calculation for computation, how we found out each of these, the cardinality of each of these sets was more or less similar. We just wrote, we figured out how many e's should be then there in each of the e run, and then how many o's should be then each of the o run by writing those equations and evaluating the number of solutions, right. So, that was the thing. So, and then yeah, now I think we complete the discussion about some examples about the multisets there. Yeah, so see, remember the question we were considering is that there are n objects. So, you can say n type of objects, and then we were making R a set of R, an R set from this thing, but in this R set everything is not distinct, it is a multi-set. That means, these objects can repeat, or mean, because if you are considering type of objects, then a particular type of object can repeat several times, that is what it says, right. But then we assume that it can repeat any number of times in it. So, infinite number of times is what we say, but actually we do not need infinite. If as long as each thing can repeat r times, that is enough for the formula we develop. That means, r plus n minus 1, choose r. This formula to work, because infinite number of what? Infinite number of finite number, we cannot take any objects more than r times, because anyway we are selecting only r things. So, that is as good as infinite for us, right. So, therefore, as long as there are r copies of each object, each type of object, that is more than enough. So, therefore, this formula will work, but on the other hand, if the number of object of certain type are less than r, then this formula will not work, and we will discuss this problem later, and we will come back to that, but it is not easy to get a general formula directly. We will try to find out some ways of dealing with that problem later. Okay. So, now the next issue is, this is something like which we have to be bothered about. How big is this n choose R? Of course, we can prove identities, we can say that we can take a problem and show that the total number of things is some 100 choose 20, but then these numbers are not the usual numbers we use. So, this is something like we know that this is 100 factorial divided by 20 factorial into 80 factorial, but then it does not make any sense, right. How big will be this? Okay, of course, I cannot get a feel of what is 100 factorial, but still that number is just a product. We would rather, we are more familiar seeing certain numbers of the form 2 to the power or maybe 10 to the power and things like that, right. So, it would be nice to compare with more familiar forms then. So, once n choose R is given, it would be nicer to know how big it is to get some upper bounds. I mean, at least I know that this is not more than this and this is not less than this and things like that, upper bound and lower bound, right. This is what our next interest is. So, this is what we are going to do. So, let us say see, of course, most of the time when you are just studying for examinations, it may not be like very relevant probably, but then if it is not in your syllabus, of course, but when you start doing research, in many cases, in many practical cases, we will have to know a little more about how big this stuff is. So, n choose R is good enough for some person as long as he is not bothered about how does it compare with more familiar forms. So, here we want to, especially we want to compare with n raised to R kind of forms, right, or something raised to the R that seems to be more familiar. One can argue why is it more familiar. Is it, for instance, if I always work with n choose R, will I get more familiar with n choose R? Probably, but still like intuitively it looks like the n raised to R kind of forms are more familiar. Therefore, we will try to come up with some upper bounds and lower bounds for this thing in terms of such powers. So, here the lower bound we are going to give is n by R to the power R, and the upper bound we are going to give is E n by R to the power R. E is the usual E. So, the constant E, and n by E to the power R, and n by n choose R is less than equal to E n by R to the power R. So, here you see that the lower bound is n by R, the upper bound is of, see, the lower bound is n by R to the power R, the upper bound is E n to the power R is E to the power R into n by R to the power R. That means it is E to the power R more, right, E to the power R more. So, this is, we are saying that this is sandwiched in between these two quantities, this and this. So, in this gap of see, this is multiplied, this lower bound is multiplied by E to the power R, that much big. So, in between somewhere this stays. So, many times this is very handy to use, therefore, we will prove it. So, let us look at the lower bound, name first n R is greater than or equal to n by R to the power R. How will you prove it? So, what is n by R to the power R? This is n by R into n by R into n by R into, like that we have to write several times. How many times you have to write? The number of times we write this is R times, okay, and this is less than or equal to n by R into n minus 1 by R minus 1. Can I replace this number by this and say that it is getting bigger? So, what I am planning is every from the first term I am keeping it just like that. Here I copied it. The second term I am replacing with n minus 1 by R minus 1. So, if this n minus 1 by R minus 1 is bigger than n by r, then we are okay, we are putting this greater than equal to here. So, it is only becoming bigger here. This will be replaced by something like n minus 2 n minus 2 by r minus 2 and so on, right. We have to show that at every stage we are replacing with a, every term is replaced with a bigger term. So, now for instance, you see in general n, we want to show that n by r is less than equal to n minus 1 by r minus 1. You just multiply like this and this is multiplied, you get n into r minus 1. We want, if this is correct, the earlier one is also correct, r into n minus 1. So, this is what nr minus n is less than equal to n minus r. So, cancel this off. So, this here, that means if r is less than equal to n, right. Yes, it is, because whenever we say n choose r, so we mean r is less than equal to n. Okay, at least in the case up to now we have discussed n and r both are positive integers, and then when r is bigger than n, of course that will be n choose r will be 0. We do not need all these bounds. So, therefore, we are only thinking about reasonable case, namely n is bigger than r, right, n is a positive integer and r is smaller than equal to n. So, therefore, we have this thing, therefore, this is true, and therefore, this is true, right. So, therefore, and therefore, the next one, of course, we can, instead of n, if we take n minus 1, this will be less than equal to n minus 2 by r minus 2, and then it will be less than equal to n minus 3 by r minus 3 and so on. We can keep on going. So, n minus right, how many times we have n minus r plus 1 by 1, right. So, r times we go, this will keep on increasing. So, that is what we are saying. So, here we can do this n minus 2 by r minus 2, and then next one will be this is this, the next one will be replaced by n minus 3 by r minus 3 and so on. How many terms are there? R terms are there, right. So, then this will be, the last term will be n minus r plus 1 divided by r minus, right, is starting with, that will be just 1, right, r minus 1 just 1. So, above what you get is n into n minus 1 into n minus 2 into n minus 3 into n minus r plus 1, and below what you get is r into r minus 1 up to 1, that is r factorial. This is therefore, we get n by r to the power r is less than equal to, maybe we can use this one, n by r to the power r is less than equal to n into n minus 1 into n minus r plus 1 divided by r factorial, which is essentially n choose r. So, that way the lower bound is proved. Now, to this is the lower bound, right. Now, to the upper bound is this n choose r is less than equal to e into n divided by r whole power r. Compared to the lower bound we proved, this is e to the power r more. That means, when you multiply this lower bound by e to the power r, we cross this n choose r is what we are saying, we go beyond that n choose r, right. So, how do we prove this thing? It is a little trickier than the earlier one, that was just direct substitution. Here what we do is we start with something like we have an inequality. So, 1 plus t, this is now that we are taking from calculus, we will not prove this thing, this is very well known, 1 plus t is less than equal to e to the power t. So, we start with e to the power t and power it by n, right. So, we can power it by n, that means here an n will come, right. So, that is what, if we power by n here, then an n will come here. So, this is greater than equal to 1 plus t to the power n, right. But then now this can be expanded using the binomial theorem, which I learned, n choose 0 into t raised to 0, and then n choose 1 into t raised to 1 plus n choose k into t raised to k, and all the way to n choose n into t raised to n. All right. So, this is the sum. Now, these are all positive terms, n choose 0, n choose 1, n choose k, everything is positive term, and then yeah. So, if you give a positive value to, suppose you are planning to give a positive value to t, so then these are all positive things. So, therefore, we can write, we can say that any individual term I take from here, for instance, if I take this term, right, that is going to be less than equal to this. So, I can write like I just take this term, and this is less than equal to 1 plus t raised to n, that is less than equal to e raised to t n. So, this is e raised to t n greater than equal to 1 plus t raised to n is greater than equal to n choose k to the power t raised to k. Now, take a positive value for t equal to say k by n, k is positive, n is positive, put t equal to k by n, then what will happen? Sorry, no, sorry, we will take, I just say I just change the variable, I will, so here I will take r, so r t raised to r. Okay. Now, put t equal to r by n. So, when you put t equal to r by n, here you are replacing by r by n whole power r, then yeah. So, this is n choose r into r by n whole power r. Here what will happen? For this t we have to put r by n. So, this entire thing will become, yeah, right, t is equal to r by n, r by n into n, this will cancel off, right, this will cancel off. So, this will turn out to be e to the power r. So, I can write it e to the power, sorry, e to the power r, this is what is coming from here, and now is greater than equal to, this we can discard here, n choose r into r by n whole power r, right. Now, we can bring this to this side. So, what we get, n choose r is less than equal to e power r into n by r whole power r, right. This means e into n by r whole power r. This is going to be the, upper bound, right. So, we have proved a lower bound for n choose r and upper bound for n choose r. Of course, but one for instance, n choose r is very important, it keeps appearing in various places. So, therefore, the special this upper bound and lower bound comes very useful. So, it is good to remember it. For instance, if you really work on research problems, many times we will have to substitute this to make sense of what we are doing. So, yeah, it is very handy, it is very easy to use. So, but on the other hand, if you insist that okay, tell me something more precise. So, this is the n choose r was this, right. So, in principle I should substitute something for n factorial, substitute something for r factorial, and substitute something for n minus r factorial, and if you do the manipulation we will get something, right. This is what will, for instance, one may ask, suppose sometimes I have a multinomial coefficient, something like n factorial by n1 factorial, n2 factorial. So, what will I do for this thing? So, you tell me something which I can use in all these situations. That means n factorial should be substituted by something, all these factorial should be substituted something. So, in this case what we can use, which is generally very useful to remember, is something called Stirling's formula. So I'll show the formula so that it is easier than writing it here. So this n factorial is approximately equal to n by e whole power n into root of 2 pi n. So you can also write it n by e whole power n into root of 2 pi n. So or you can write, so n factorial is equal to root of 2 pi, this is the constant coming here, and n to the power, we have n to the power n plus half, that is this n raised to half is coming as n here in the root in the earlier expression, e to the power minus n, this is another one. So this, so here this e was written n by e, right, n by e whole power n. So this half was taken inside the root, right. So but here we separate the constant and the dependence on, so n to the power what and e to the power what, right. But this is only approximately equal to, this is not equal, this is approximately equal to. What we say is this two sides, if you consider this right side, RHS and LHS, if you consider, and the ratio of these things, these two quantities, n factorial on one side, n factorial divided by this quantity root 2 pi into n to the power n plus half into e to the power minus n, this ratio will tend to 1, right, as n tends to infinity. That is what we see. That means as n becomes larger and larger, the ratio will tend to 1. That means they are almost equal, but on the other hand one should not think that they will become equal actually for some very large n, it will never become equal. In fact, if you are considering the difference between the two sides, that means n factorial minus root 2 pi into n raised to this one n raised to, maybe we can this formula, right. See, n factorial minus n by e to the power n into root 2 pi n, that will become arbitrarily large as you go bigger and bigger, n becomes larger and larger, this gap will become bigger than any fixed number. For instance, you can say that will it become bigger than 1 million? Yes, it will become bigger than 1 million. So any number, any large number you can fix, it will go beyond that, it will grow right arbitrarily large, but the ratio will tend to 1 is what saying. The difference is difference may grow, but the ratio will tend to 1, right. And therefore it is so many times it will be quite useful with that kind of approximation also. You see, this data I have taken from the book of William Feller. It's he has given this values, right, for 1 factorial. For instance, if I evaluate the other side, so for instance this is put n equal to 1 and I evaluate the other side, that means root 2 pi into n raised to, so 1 raised to 1 plus half into e raised to minus 1, then it is like 0.9221 approximately. So here he says the percentage error in the sense of this divided by for instance you take the difference between the two divided by what you are actually calculating, that will be 8%, but when you do 2 factorial, the percentage error reduces to 4, 1.919 is the value which we get for this quantity when you put n equal to 2 to the power, but actually we should have got what 2 factorial is 2 only, right. So we are getting 1.919, right. There is a difference, but the percentage error has become lesser compared to what it was in the first case. But when you go to 5 factorial, value of 5 factorial is 120, but we will be getting 118.019. So something slightly smaller than, the difference is slightly smaller than 2. So if you find 2 by 120 and find that error, it will be something like percentage, that will be something like 2%, yeah, approximately. So now the now we go to 10 factorial. So, the percentage error is decreasing steadily, and when you go to 10 factorial, the value is this one 3 million sorry. So, 36 lakh 28,800, right. So, here we will get if you evaluate the other side, this side we will get something like 35 lakh 98,600. The percentage error has gone down to 0.8 here, but on the other hand you see the difference is increasing, but the percentage, the ratio wise it is getting closer and closer to 1. When you go to 100 percentage 100 factorial, the ratio is becoming, the error is reducing to 0.08 percentage, right. So, it is better and better is what the claim is. And now of course, we have this question now, how we are going to prove it, right. Is it easy to prove? So, I would, so usually I do not have to prove it, because you see it is enough to remember this formula, but again maybe to give a feel of how the proof goes, maybe I will indicate how, yeah, it is. So, for instance, so we can, there are two sides here, right. So, one is say n factorial, one is n factorial, the other side is our root 2 pi into n raised to n plus half and e raised to minus n, right. Now, so sorry, these are two sides, we are saying approximately this is equal. Now, what we do is we can work with say log of n factorial, we can work with log of n factorial, and then yeah, with log of n factorial when we work, so we can compare the quantity with, yeah, how will you do it? So, do this thing. So, we will say that, so consider this integral, right, log of, so for instance k minus 1 to k, you can try to integrate this function log x, right. So, k minus 1 to k. So, of course, this log x keeps log of k minus 1. So, and when you keep increasing the value of k, it will slowly increase, right. So, therefore, this is going to be less than equal to log k, right, and this is also less than equal to log yeah. So, for instance, right. So, this is for k minus 1 to k log x, it will be less than, we do not have to put less than equal to, less than log k, and that will be less than equal to, for instance, we can take it from k to k plus 1, right, this will be correct. So, we have to integrate dx, right. So, now right. So, therefore, k minus 1 to k when you integrate log x. So, that will be definitely less than log k, because this is the last k, and then k to, because this quantity is going to be bigger. Now, this can be done for instance, when we put k equal to 0, sorry, k equal to 1, this is going from 0 to 1 log x dx, right, and from here it is from 1 to 2 and so on, right. So, you can sum this thing for k equal to 1 to n, then what will you get? This will go from 0 to 1, 1 to 2, then 2 to 3 and all the way up to n. So, this will totally this will become an integral from 0 to 1 to n log x dx, right. So, now this will be less than equal to log of n factorial, because we are this is log 1 into log 2 into, right. Of course, it is almost time. So, we will stop here.